Good afternoon, everyone, and welcome to this webinar of CLINT and MedEWsa. We will wait for a couple of minutes for people to join, and then we can start. We will still wait for one more minute, and then we can go. Okay. I guess we've been waiting already for a couple of minutes, and we can start. So to everyone who is attending, welcome to this webinar organized by the projects CLINT and MedEWsa. This is Antonello Squinto. I work at the CMCC, and online you see Yiheng Du, which will present this webinar. Before starting, I will give you a short introduction to the CMCC, to the activity, and I will share my screen so that you can see my presentation. One moment, there it is. I hope you all can see it. And good. So CMCC is hosting this webinar, and I'll give you a presentation about who we are and what do we do. And so we are a leading research center. We focus on understanding interaction between climate change and society. So here you see a summary of all the institutions that cooperate with us and in which we work. We are a no-profit foundation, charitable organization under the Section 501(c)(3) of the US International Revenue Code. So what do? We work, and our activity brings from the mission, bringing from models to solutions, advancing climate research through multidisciplinary analysis, combining climate modeling, impact assessment, and environmental economics, and supporting science-driven adaptation and mitigation actions. Yeah, I'm sorry. Something, okay. I am going to, okay, sorry. So our research infrastructure is transversal and multidisciplinary competencies that combine first-class climate modeling with climate change impact modeling, environmental economics. There are 3 multidisciplinary research institutes, 4 strategic programs on frontier topics, a computing infrastructure dedicated exclusively to the study of climate change, 2 specialized centers on digital innovation and high-level education and training. The research institutes are the Institute for Earth System Predictions, which works on the leveraging climate modeling capabilities and turning scientific knowledge into improved predictive tools. We have the Institute for Climate Resilience, which creates data-driven digital representation of the Earth system components to provide insights, risk assessment, and policy support tools for sustainable climate resilient development. And then finally, the European Institute on Economics and the Environment, evaluating sustainable and socially enhancing climate strategies at the intersection between environment, technology, and economy. Our strategic programs, we have 4 of them. We have integration of the planetary biogeochemical and industrial carbon cycle, which models carbon cycles to support the transition to a low-emission economy. The Global Coast as a New Frontier, which develops digital twins to explore coastal phenomena at the intersection of physical and economic processes. The Predicting Socioeconomic Impacts of Climate Change strategic program, which aims at developing integrated models to support adaptation within policy and investment timeframes. And the last strategic program is the integration of artificial intelligence and machine learning in the modeling chain, leveraging data-driven approaches and machine learning to enhance modeling and analyze large-scale data. We have 3 centers: the High Performance Computing Center, the most powerful computational facility in Italy and one of the most advanced in Europe, which are fully dedicated to climate change research. The Advanced Digital Innovation Center, which is a transformative hub bridging cutting-edge technology with the critical research needs of the future. And the Advanced Training and Education Center, which provides education training, exchange, and knowledge transfer on climate change. This webinar will be structured as follows. So your audio and video are deactivated by default. You can intervene with a Q&A section, which you should see in the chat here on Zoom. You can type your questions also during the webinar while Yihang is presenting. At the end of the presentation, we will read out loud the questions for Yihang, and we will start the discussion. This video, this meeting webinar is recorded, and you will soon find it on the CLINT and MedEWsa website. And so I will now give a short introduction about Yihang, which now works at the SMHI in Sweden, in Norrköping, after her studies on water resources engineering in Nanjing, then at Lund University, where she completed her PhD. She is now indeed at the Swedish Meteorological and Hydrological Institute, and her work focuses on the seasonal hydrological forecasting, the use of artificial intelligence, and also large-scale hydrological models. I will now stop sharing my screen, and the floor is for Yihang for your presentation, so you can share your screen. And yeah.
Thank you. Well, now you can see my screen.
We do. You are in presentation mode? Okay, now it's perfect.
Does it work? Okay.
Yes, thank you. And yeah.
So, thank you. First, I need to say good afternoon, or good morning, or good evening, just in case you are joining from a different time zone. And firstly, I would like to thank you for this opportunity to connect with you all, that we all share a common concern of water-related risks. So today I will be talking about our efforts in hydrological predictions and how we are using AI to enhance our current services across Europe. And this work is a joint effort between myself and Dr. Elias Pachnivanidis, with contributions from our colleagues at SMHI. So nowadays, AI has been more and more recognized for its incredible ability to detect complex patterns. And many researchers and experts are already working on it to implement AI for water-related challenges. And we are happy to be actively involved in these projects. For example, CLINT, focusing on extreme event detection, prediction, and attribution, and MedEWsa, its aim to develop an AI-based operational early warning system. And one achievement of our work for these 2 projects is a framework of hybrid modeling, and this framework was established and tested under CLINT, and we will be working on its operational implementation in MedEWsa. Besides this, we are also contributing to the global initiative on resilience to natural hazards through AI solutions as a case study to show AI's application in hydrology. And now part of our work is summarized in a scientific publication, currently still under review, but it's available openly as a preprint. So we'll welcome your insights and feedback on it. Now, please allow me to walk you through the structure of today's webinar. We will cover two main sections. First, the challenges. We will begin by talking about the increasing demand for hydrological forecasting services and introducing the forecast production chain and large-scale hydrological modeling. And of course, the challenges that arise from these processes. And then we will present our solution with AI enhancement at local scales. We will evaluate the performance of this approach for total volume and extremes, which are both critical for water resources management and early warning systems. Then we will discuss how we can extend these improvements to ungauged basins, and finally outline our roadmap for its operationalization at subseasonal to seasonal scale. So let's start with the once upon a time part of today's story, which is the understanding the risk. So when we talk about risk, we are actually talking about three elements: the hazard, exposure, and vulnerability. Without any one of these three, there is no risk. And nowadays, unfortunately, the hazards part, such as floods and droughts, they will be intensified due to climate change, both the frequency and severity. And at the same time, the exposure will also be increasing as the growing population and the expanding urbanization. So more people and critical infrastructures will be potentially affected. So now this leaves us with one factor to act upon, that is the vulnerability. So to reduce risk, we need to strengthen the capacity of our communities to handle these hazards. And this is where accurate forecast becomes important, because the decision-making and actions, they all depend on reliable information. So now let's take a look at how hydrological forecasts are generated. Here I'm showing the production chain of our subseasonal to seasonal hydrological forecasting system. We start by taking dynamic meteorological forecasts. For example, for seasonal forecasting, we use the daily precipitation and temperature from ECMWF CIS5 meteorological forecasts. And these forecasts will then be bias adjusted and used as inputs for our hydrological models to generate hydrological forecasts. We provide both hintcast, which allows us to evaluate the forecast performance, and also operational forecasts, which inform the decision-making processes. And to have an accurate forecast, some catchments, they can benefit from locally well-calibrated hydrological models. This is, of course, the ideal situation. However, in many other cases, this is not possible due to limited observations, resources, or unstable social conditions. And this is where we need large-scale hydrological models, as they can provide hydrological information even for ungauged basins. And this is important because it's guaranteeing the equal access to climate services. And this is also the idea behind all the efforts that our institute has put in developing hydrological models at both the global and continental scales. And with that, let me introduce the princess of our today's story, the eHype. So eHype is the European configuration of the HYPE model, initially developed in 2009, making it 16 years old today. It is still under continuous development and improvement. Here are some more facts about eHype. It covers the pan-European region with over 35,000 subbasins, and the average subbasin size is around 215 square kilometers. The historical simulation is driven by an in-house dataset called HydroGFD. It is a reanalysis dataset with daily precipitation and temperature. So on the right, you see the model's calibration and validation stations. And for validation, this model has a median NSE of 0.5. And now I'd like to highlight a key concept in large-scale hydrological modeling, that is the hydrological similarity. It describes how similar the basins are in terms of hydrological processes, and consider the various climatic and hydrological conditions across the whole Europe. We have categorized all the basins into 11 clusters, each of them representing a distinct hydrological regime. For example, class 1 here, you see it's mainly base flow controlled with some snow driven. And cluster 4 is responsive to precipitation with regulated in winter. So these clusters are very important. I will get back to it when we discuss ungauged basins. Just want to put a bookmark here now in your mind. So with this information in place, let's now meet the dragons, the challenges we face in large-scale hydrological forecasting. When generating forecasts, we begin by running a historical simulation, which is also called the reference simulation. And from there, we take the hydrological initial conditions at the initialization date of a forecast. Then we use the meteorological forecasts as forcings to generate hydrological variables for the forecasted period. However, here lies a challenge. These simulations are model estimates. They provide simulated conditions. As a result, the discrepancy between the simulations and actual observations will propagate into the forecasts. Here is just another way to understand the issue I just mentioned. The upper plot shows how the forecast scale deteriorates over the lead time, and this is largely influenced by the uncertainty in meteorological forecasts. Then the lower plot shows the arrows in the reference simulation, and this will further propagate into the forecasts. And at the first glance of this plot below, you might look at the figure and think, it's mostly green, which means quite good performance. And that is a very optimistic opinion, which is nice. But here, the reality is, what if we are here? If we are decision makers in the water sector or farmers at this orange points, for them, the overall performance doesn't mean anything. It's whether the prediction is accurate at this critical point where decisions are made. It's the local scale that matters. And why large-scale hydrological models often struggle at the local scale? There can be several reasons. For example, the model structure and parameters may not fully capture the hydrological processes of a specific region, or there is human intervention, such as irrigation, dam operation, and those factors are the large-scale models may not account for. So how can we improve our models to address these challenges? This is where AI comes into play. We have developed a workflow to integrate different post-processing methods, here both statistical and machine learning, to reduce the residuals in the process-based eHype model. So within this framework, we used a comprehensive evaluation that includes total water volume, high and low extremes, as they are important aspects for water resources management and disaster reduction. Then we also analyze where we get the most significant improvements and why, by connecting the model performance to potential driving factors. And here we considered climatology, physiography, human impacts, and hydrological regime. So we tested this workflow at around 2,000 gauged stations in the pan-European domain. We compared 4 different post-processing methods, including generalized linear model, quantile mapping, random forest, and long short-term memory model. At this stage, each post-processing method was trained individually for each gauged station. And the models were trained on 80% of the data and tested on the remaining 20%. And all the results that I will be showing you later are from the test periods, if not noted otherwise. So now let's look at the results. On this slide, there are cumulative distribution of model performance for all the stations based on the evaluation metrics for total volume, high extremes, and low extremes. The green line represents the performance of the raw eHype model. Then the colored dotted lines correspond to different post-processing methods. And on each figure, you can find a green smiling face, and that indicates the direction of good performance. Let's take total volume as an example. So ideally, we want to minimize the error, meaning that the best performance for total volume should be as close to 0 as possible for all the stations. But as you can see here, the colored dashed lines, if we compare them to the green line, they are more closer to 0. And this means the post-processing method reduces errors compared to the raw model. And similarly for high and low extremes, only the ideal scores here are 1. Again, the colored lines are closer to this ideal value after post-processing, meaning that the post-processing methods enhance model performance also in terms of extremes. So this is our first message. Yes, hybrid modeling improves representation of streamflow characteristics. So now we see improvement at the overall level, and we can start evaluate the performance at each individual station. Here you can see the skill achieved at each location by each method for high extremes. This is an example. The colors showing how much improvement we get compared to the raw eHype as a reference. So the bluer the color, the higher the improvement. And the gray indicates no improvement. And we'd love to see blue everywhere, a perfect score of 1 across all the stations. But as you can see, that's not quite the reality. Also, the patterns have some differences across different methods. So then we start to ask ourselves, is there one post-processing method that outperforms all others across all locations? Like the one ring in the Lord of the Rings, one method to rule them all? Here, the answer is no. In the plots below, we show the best performing method at each location. What we see is a colorful mixed pattern, kind of like a knitted sweater. So each station has its own best performing method, but no single method dominates everywhere. And on the right side, you see the color blocks showing the proportion of stations where each method is the best performing one. And here, the two AI models, LSTM with color pink and random forest in color orange, they have relatively higher proportions. So here comes our second message. Not a single best post-processor, but we see spatial complementarity. And this leads us to our next question. Why do the methods have different skills at different locations? And to understand this, we examined various potential influencing factors, including climatology, topography, human impact, and hydrological regime. And those factors are listed in the table on the right. But first, to reduce uncertainty, we checked for interdependencies among these factors. If two factors were highly correlated, such as mean temperature and mean snow depth, then we only keep one of them to avoid redundancy. And after filtering out these dependencies, we were left with 8 potential drivers for further analysis, as shown in the table. Here, if you still have your bookmark in your mind, hydrological regimes are represented by the 11 hydrological clusters. And to find the relationship between these factors and the model performance, we applied a tree-based method. It helps us identify which factors have the strongest influence on the skill improvements for each post-processing method. The heat maps here, they show the importance of each factor in each method. The brighter the color, the more important the factor is. Then we can get a final ranking based on their importance across different post-processing methods, and that is shown on the top of the plots. Now let's zoom in to take a closer look at high extremes. Here, both from the color and the ranking, we can see the highest ranking factors are the mean precipitation, mean temperature, and these two are representing climate conditions of the basins, and then hydrological clusters, representing hydrological regime. So these three are the top influencing factors for the high extremes. So how is the skill related to them? Here we can see an example here. We show the skills from eHype post-processed with LSTM and how the skill changes with the 3 identified factors. So the first plot, when the mean precipitation increases, the skill tends to decrease. And then the second plot, the mean temperature increases, the skill tends to increase too. So together, these two indicate post-processing with LSTM tends to have more improvement at basins that are warmer and drier. Then for hydrological cluster, as shown in the plot below, the skills are very different across different clusters, both in terms of the median skill and the distribution. Then we go back and see for the total volume and low extremes. And there we can see hydrological clusters are also in the top 3 influencing factors, especially for the low extremes. And another interesting observation here is the relative ranking of the importance are quite similar across different post-processing methods, which means these results are not method dependent. In other words, no matter which post-processing method we use, hydrological regime remains an important factor for model enhancement. And that is our third message here. So to summarize this section, we tested different post-processing methods, we evaluated their effectiveness, and we confirmed that hydrological regime plays an important role in the model performance enhancement. So what about ungauged basins? When we don't have observations to train an individual post-processing model, how we improve the predictions there? And here, what we do is to building on the workflow we just tested at gauged stations and extend it to ungauged basins by adding hydrological similarity. With hydrological similarity, we can establish the connections between the ungauged basins and gauged basins. And this allows us to develop a regionalized model. This model will be trained on gauged basins, but will be applied to the ungauged ones. In this way, we can transfer the knowledge from the 2000 basins to the whole domain. So how is the model trained? If you remember before what we said, well, LSTM isn't exactly the one ring that we need, but it still performs well across most stations. So that's why we choose LSTM as a candidate for this approach here. And from now on, I will refer to this model as the regionalized LSTM model, as it is trained across multiple stations. The inputs to the model have several different classes. First one is static variables. These ones, they don't change over time, and they are the descriptors we discussed earlier, such as climate conditions, topography, and hydrological regime, as listed in the table. Then we also use dynamic variables. They change at each time step, and they are from EHYPE simulation. Here we use temperature, precipitation, and runoff. And the target of the model is still model residual compared with observation. And to simulate ungauged conditions, we split the stations into training and testing sets. Some stations are held out from training to mimic ungauged basins. We then use cross-validation. So we rotate which stations are included in the training just to ensure the robustness. Then for evaluation, we compare the regionalized model against raw EHYPE. So raw EHYPE is our reference here. And then we also compared the regionalized model against the single LSTM, which are the model trained individually for each station in the previous section. So this is kind of our benchmark. So similar as previous evaluation, we also assessed the regionalized model for its improvements on total volume, high and low extremes. And this we do it for all stations together and for stations in each hydrologic clusters separately. Here is just an example of how this comparison was done. And I will just jump to the conclusion for now. If you are interested in the detailed evaluation, please contact us after the webinar through emails. We will be happy to have more discussions around it. And here the conclusion is the regionalized model provides improvement at both gauged and ungauged basins because it outperforms the single LSTM model during the testing period for gauged stations. And more importantly, it also has added value at ungauged basins, which means it has ability to generalize beyond the training data. So based on this, we will continue with more assessment of model performance. But from now on, we will shift our focus from the evaluation metrics to flow signatures. In our work, we evaluated for 3 signatures, which are crucial for long-term water resources planning, especially at the seasonal scale. And that is mean flow, which is a long-term average, and then Q90s, that is the 90th percentile, representing the high extreme condition, and then Q20, which is the 20th percentile for low flow conditions. And due to the limitation of the slides, I will just take Q90 as example. And again, any detailed discussions are welcome by contacting us. So if we look at the patterns here from observation, raw E-hype, and then AI enhanced by the regionalized model, we can see there are areas where the raw E-hype tends to miss some key patterns there, like we showed in the boxes. But after applying AI-based post-processing, we see clear improvements there. For example, Norway and France, the AI-enhanced model, they capture these patterns more clearly. And this brings us the second message for ungauged basins. Regionalized model improves the representation of hydrological signatures. Now let's check more closely for each station. We are showing the scatter plots. On the x-axis, it's the observation, and then on the y-axis is the model simulation. We have raw E-hype on the left and AI post-processed outputs on the right. And to have a more detailed evaluation, we also color the dots by its hydrological regime and get the linear trend lines for each hydrological cluster. So in the raw E-hype simulation, which is on the left, we see a systematic shift away from the one-to-one reference line. And that means there is a mismatch between the model simulation and observation. Then after post-processing, both for gauged and ungauged stations, the points move closer to the reference line. And that means the corrected flow signatures, now they better align with observations. And what's more, not all the clusters respond similarly. Some show greater improvements than others. For example, cluster 4, which is the line in dark green. And this again showing the importance of hydrological regime in the model enhancement we can get from post-processing. which is this message. Next, we apply this regionalized model to all the catchments, and that gives us updated patterns for the flow signatures. Here, still using Q90 as the example for the high extreme. Since we are now dealing with ungauged basins, so we no longer have direct observations, we can still analyze how the AI-enhanced post-processing changes the patterns produced by the raw E-hype. So in the plots, the brighter area with yellowish colors has higher flow signature, then the blue color has lower signature. And to visualize the differences before and after post-processing, we also plot the signature along latitude and longitude on the margins. So there we see where the most significant changes occur. And from these plots, the first finding is in some areas, the high flow signatures become more pronounced after post-processing, such as Norway, France, Switzerland, and there are areas also along the Mediterranean Sea. Notably, these are also the regions where we previously observed underestimation in the raw E-hype simulations. And then another interesting observation is compared to the smoother spatial patterns in the raw E-hype, the post-processed patterns, now they have more localized variations. There are areas stand out more distinctly, for example, in the Eastern Europe. And that means that AI enhancement is capturing finer spatial patterns based on the extra information, including climate conditions, hydrological regime, and the others. So with that, I come to the last message of the ungauged basins. AI enhancement provides updated pattern of hydrological signatures. To summarize this section, we tested a regionalized approach, which showed its capability to improve E-hype simulations across different flow signatures. And by applying this method across the entire domain, we get an updated pattern of flow signatures. Then we move to the next step, the operationalization. And we plan to introduce one additional step after regionalization as part of our ongoing efforts within MedEWsa. If we're going back to the forecast production chain, now that we have the potential to apply a post-processing for all catchments, then we will integrate a post-processor in this production chain, and this step will generate AI-enhanced forecasts, and this will provide more information for decision-making. But of course, before this approach can be fully operational, there are several important evaluations that we need to do. We need to assess the performance of the AI enhancement in a forecasting setup, because now it is still evaluated for the simulation. And also for the ungauged basins, more investigation is absolutely needed. But for this, we can potentially adding new monitoring stations or using other data sources, such as remote sensing, for example. So still a lot of exciting work ahead, but we are looking forward to it and looking forward to collaborations around it. Now I bring you back to the outline of today's talk. We've been on quite a journey starting with the challenges in large-scale hydrological forecasting, where we discussed model imperfection and the importance of hydrological similarity. From there, we explored solutions addressing both gauged and ungauged basins at the local scale, and also laying out our plan for operationalization. I hope I have been able to communicate the key messages. And as I mentioned, there are still uncertainties when moving from gauged to ungauged conditions, and these require further validation. And just a final thought before I end my talk. I think for any kind of problem, AI won't just jump onto the stage and slay the dragon for us. We are the chosen ones. AI may be our sword, but it is us to use it wisely and solve the hydrological challenges ahead. So thank you. And now I'm looking forward to your insights.
Thank you very much, Yihan. It was a very insightful, and it was very interesting to follow all your work. I now invite all the attendees that want to formulate their questions in the Q&A box, and we will read them out loud, and we will start a discussion. In the meanwhile, I think I have a couple of questions for you. I will start from a rather, which is both a curiosity and a technical question, because I noticed in the when you were outlining the starting point of your research, I noticed that both because of sparsity of the station in Southern Europe, like I saw Iberia, Cyprus, Greece, and Italy, the low scale from which you start for the gauge station. Correct me if I'm wrong. So these mostly, but these are also those that experience a larger increase of skill, right?
Yes.
And these are most of the times arid areas with low precipitation, probably, or maybe more seasonally driven. So I wanted to know from your opinion how these has influenced, because they were also belonging to different clusters, if I'm not wrong. So how did this influence, in your opinion, the workflow of your AI models? Or
so for the stations, first I need to say we had a filter of the stations, and that is based on the data availability. So we need to have at least 10 years of data so we can train the model on. And for the areas with initially low skills, low performance in the raw E-hype, and we think some of the basins, especially in Spain, for example, there are many basins that are regulated, and we also noticed that when we check the Streamflow time series. So the raw E-hype model is not capable of simulating these unnatural patterns, but some of these are improved through the AI post-processing. And when we check the driving factors for where can we achieve a higher skills, there we also noticed the mean precipitation and mean temperature. So that's, as I said, I think it's the warmer and drier basins we usually receive higher model improvement, and that is also the places where the raw E-hype has initially lower skills. So
I see. Yeah, then also you highlighted the different AI post-processing methods that, yeah, they work differently on different stations. And but then how do you, and maybe you can elaborate on that, how do you decide which one to use on specific region or hydrological cluster? Or maybe there's so what is the criteria for this decision?
No, we don't have a, so for from the gauged station experiment, we didn't choose any method across. So from these different methods, we just want to do a comparison, and by applying different methods, we also want to find some underlying common patterns, which we find for the drivers. And also from this spatial complementarity among different methods, we also think the future direction is maybe a multimodal ensemble method. That would be good, because then we can take advantage of different methods. Yeah, that is just some thoughts for this.
I see. And then when you move to the regionalization approach, no? And then this is also, and it also allows you to cover regions where you don't have, of course, by definition, stations that can. So, did you see any, like how well the regionalized model was able to cover? Because as we saw in your graphs, that there was an improvement in both cases, and this was is it one of the powerful aspects of the regionalized model to cover also regions where you don't have availability of data, correct?
Yes.
And yeah, but then when you already have a gauge station, and maybe the single model is that the case? I cannot remember exactly where the single model still works better than the regionalized or not. And then would you still prefer also maybe for operationalization purposes to keep the regional model, or would you opt to use a single model? How does it work in the perspective or operationalization of these?
Yeah, so I didn't show the detailed results here, but in one of the lines, we showed the testing period for the gauged stations, and there, the regionalized model, either it shows similar performance with the single, so individually trained model, or in specific clusters, it actually outperforms the single model. And we think that is because maybe one reason is the regionalized model, it is trained on more data. So it gets more information, and then it also learns the patterns from other similar basins. So that's why for the operational part, we think the regionalized model, since it shows its capability in both gauged and also ungauged conditions, so that's the one that we will be using. We'll be working on it.
Okay, then I have my very last question, and then we will close this webinar. And this really goes into also in the perspective of what the projects CLINT and MedEWsa, which is a joint webinar of CLINT and MedEWsa. So the operationalization of AI enhanced models it's not trivial. And what do you think are the key challenges that come from the uncertainty of these methods, also for the real-time decision making that is the final goal of this kind of application? So I'm curious about your opinion about these.
Yeah, I think so to operationalize, and then there is still a gap from we actually operationalize it until the decision makers can actually accept the information from AI enhanced post-processing forecasts. So in between this, we need to understand why we get these improvements from AI, and then we also need to test it in a, I would think to test it in a continuous operational mode. So to test it, to validate it with the real operational forecasts and the real-time data before we use it and launch it for decision making. Because I think we need to understand the method more and to build our trust for it.
Well, Yang, I thank you very much for your presentation, for the great quality of your research, and I thank you all the attendees for to be here with us today. I still thank you also for the work of CLINT and MedEWsa, and I wish you all a good afternoon or evening or morning, wherever you are. Thank you, and
thank you.
Bye, Ian.
Goodbye.
Goodbye.